Model selection. So when you have potential predictors, which one should you include in your final model? You have various potential predictors, and you're trying them. What should you include in your final model? So the goals of model selection. Model selection means selecting the best model for your case. And first of all, parsimony, the simplest models that adequately explain the data. You want to get a model that is very simple but explains the data. So if you have 20 predictors and you have an adjusted R square of 0.3, and you now have 5 predictors on adjusted R square of 0.9, you can see that model with the 5 predictors is simple but explains the data more than the one with 20 predictors and the adjusted R square of 0.3. So you need to find the simplest model that adequately explains the data. Prediction accuracy also, you need to find the best predictive performance. The one with the best predictive performance, and also the model interpretability, the model that is understandable and meaningful both in real life and theoretically. And also you need to find a model that avoids overfitting. So the model should not fit noise in the data. The difference between residuals and your predictors should not be very high. It should be very minimal. The difference between your residuals and actual values should be minimal. So the bias variance trade-off. Too few predictors. When you have too few predictors, you have high bias, so you have underfitting. When you have too many predictors, you have high variance, you have overfitting, and your goal is to actually find the sweetest spots. So you want to have plenty predictors, but with moderate fitting. So we have various information criteria for actually comparing models. So we have what we call the AIC. So the Akaike information criterion is usually used to compare models. So the higher if you have an higher AIC, so we have 2 AIC from 2 models, you have to choose the one with the smallest value. So this is just the formula, but you don't need to calculate this. R is going to calculate that for you. We have likelihood of the model, we have the number of parameters, predictor plus the intercept. So the lower AIC now is a better model. When you have 2 more AIC, the one with the lower AIC is actually the better model. So when the difference between the 2 AIC is less than 2, it means that the models are essentially equivalent. But if the difference between the AIC is between 4 to 7, it means that considerably less support. And the difference between the 2 AIC is greater than 10, it actually means that what? No support. So we also have the BIC2 also. The BIC, this is also the formula. We have the likelihood of the model, the number of parameters, and also the sample size. So the BIC2 also, the smaller one is usually the better model, but its actually penalty is larger and it penalizes complexity more heavily than the AIC. So the BIC is the Bayesian information criterion, and it tends to select simpler models. So we have n greater than 8 and your log n greater than 2. So the BIC penalty is greater than the AIC penalty. So which to use? Use the AIC for better prediction and use the BIC for finding the true model. So we have various ways of selection methods for model predictors. We have the forward selection. So the forward selection, you start with no predictors, just your intercepts only. Then you add a single predictor. If you see that the single predictor improves the model, you start by adding a predictor that improves the model fit the most. This can be possible from various literatures or maybe after testing each particular predictor individually. Then you now keep adding these predictors one at a time to your model. Then you now stop when you find out that no predictor is improving the model significantly. So this is called the stepwise selection method. The stopping criteria is usually the p-value threshold, or you can use the AIC or the BIC to compare each models that you have already added. So a model with 2 predictors will compare with the model with a single predictor. So you can compare them with the AIC and the BIC or use the p-value threshold. We have the backward elimination method. So the backward elimination method starts with the predictors in the model. Then this time around, you start with all the predictors. This is opposite of the forward. Then you remove the least, you run the model, then you now remove the least significant predictor. Then you keep removing predictors till you found out that all the remaining predictors are actually significant or the model is not even necessarily increasing. So this is opposite of the forward selection method, and you can also compare them with the p-values, the AIC, and also the BIC. Then we have what we call the stepwise, which is bidirectional. You are trying now to combine both forward and the backward selection. So at each step, you can either add or remove predictors, and this is more flexible than the forward and the backward. And you can also reconsider previously added or removed variables. So the criticism of the stepwise method, statistical problems, is it actually inflates the type 1 error. Probability of rejecting the null hypothesis when it's actually true. So standard errors and p-values are usually too small the coefficients can be biased, and also the model uncertainty is not actually accounted for. These are some of the statistical problems with the stepwise methods. And also reproducibility issues. Small changes in data can lead to different models, and it is not stable across various samples. So because it's a complex method, you are adding, you are removing. So these are some of the criticisms that the stepwise method actually have. So we have alternative approaches such as theory-driven selection. You let scientific knowledge guide model selection. You don't just add or remove predictors anyhow. You have to look at previous literatures. You have to look at real-life case studies. What are actually predictors for your outcomes. This, you have to include variables based on previous research. Consider confounding and causal relationships. You also have to include predictors regardless of statistical significance if they are theoretically important. So even though a predictor is not statistical significance, you try and add it if it is actually theoretically important, because it's possible you can confound another predictors inside that particular model that you have. So alternative approaches, we have all subset regression, whereby you test for all possible combination of predictors. It is actually exhaustive but computationally intensive. So with P predictors, there are 2 P possible models. So if you have P predictors, you can have 2 raised power of P possible models. So if you have that, let's say for example 2 predictors, now we have We can have 4 models. So either a model with the 2 predictors, or a model with the first predictor, or another without the other one, or a model with the second predictor without the first one, or a model with none of those particular predictors. So that's what we mean by 2 raised power of P possible models. So we can compare using R-square, adjusted R-square, AIC, or the BIC. So we have regularization methods. So lasso regression, L1 penalty, it can shrink coefficients exactly to 0. It performs automatic variable selection, and it is useful when the P is actually large. So we have new methods, we call them regularization methods. These are beyond the traditional selection that shrink coefficients towards 0. So the lasso regression shrinks coefficients exactly to 0. It performs automatic variable selection, and it is useful when the P is actually large. So this is for the lasso regression. We call the L1 penalty. So coefficients that are naturally significant, it shrinks them to 0. And we have the ridge regression, which shrinks coefficients but does not eliminate them. So lasso regression will shrink and eliminate those ones, but this one is going to shrink them but will not eliminate them. So it's usually useful when predictors are correlated and does not perform variable selection. We also have the elastic net, combines lasso and ridge regression, and it's usually the best of both worlds. So these are complex regression techniques whereby you use when you're trying to find out the best models for your data. So some practical recommendations. First of all, you need to start with theory. You have to understand your predictors. You have to know which values are actually predicting, which are your confounders, which are your mediators. It's very important for you to select the best model. Also, it's important to use your VNF to check for multicollinearity. You also plot your correlation matrix to find out where correlation happening among your predictors, and you remove highly correlated variables. Also, in terms of interaction, you test theoretically plausible interaction, inclusive, significant, and meaningful. And also, you should use your AIC, BIC, and adjusted R-square to compare various models together. So the overfitting problem, say a model that fits the current data perfectly may perform purely on new data. So in terms of this, we have what we call the k-fold cross-validation. You split your data into k subsets. You train your model on various folds, then you test on the remaining fold. So you're going to be repeating this particular k times, and you take the average performance across each fold. So after splitting your data, you train a model on a particular split, which is k minus 1 fold. Then you now test it on the remaining fold. So you repeat it for each particular fold. You train a model in another fold, you test it on let's say you have 10 folds. You train on the first fold, you test it on the remaining 9 folds. You train on the second fold, you test it on the remaining 9 folds. You train it on the third fold, you train it on the remaining 9 folds. You repeat this until you have average performance across folds. So this is more or less like a machine learning technique, whereby you hold out a portion of your data, you build the model on training set, you also evaluate performance on test sets, and your test set simulates new data. So the model selection, this is summary. Parsimony, always simpler models are preferred if they fit adequately. So this is called the outcomes results technique, whereby you try something. The simplest is actually the best. So context matters. Selection criteria should depend on your goal. So prioritize predictive accuracy, prioritize interpretability and vary standard errors, and also include confounders regardless of significance. Also, avoid data dredging. Don't let the data alone determine your model without theoretical justification. And also be transparent about how you selected your final model. These are things you should put when you're trying to explain how your model. So building a multivariable regression model requires statistical knowledge, understanding the methods and assumptions, also subject matter experts, knowing what makes sense in your field, also critical thinking, questioning results and checking assumptions. And you also need honesty, reporting methods transparently. So you need to understand the method and assumptions you are using. You need to know what makes sense in your feed. You also need to question results and check your assumptions carefully. If a particular variable is significant and is not significant in practice, then you need to find out what is going on, what is wrong. You also need to report your methods transparently. So remember, a model is a simplified representation of reality, and all models are wrong, but some are useful. So it's just a simplified representation of reality. All models are wrong, but some are useful.